Hello viewers, welcome to the fourth lecture of AC Fundamentals. Today we are going to start with RL series circuits. Before that, let me talk about the lagging and leading concept. Okay, up to the previous sections we have seen purely inductive circuit, purely resistive circuit, purely capacitive circuit. But practically this is not feasible because every coil may be made up of very best material. It will have its own resistance, right? So even if we say whenever we say it's an inductive coil, it is basically an RL series circuit. Okay. Similarly is the case of purely capacitive circuits, etc. Okay. So a purely inductive circuit, purely capacitive circuit, purely resistive circuit is a myth actually. Okay, so frankly speaking, we have RL series circuits, RC series circuits, and so on. Okay, so the very first of them today we are going to deal with RL series circuits. Okay, by this lecture, what we have seen is in case of resistive circuits, voltage and current are in the same phase. Purely inductive circuit, the voltage leads the current by 90 degrees, or more precisely we normally say inductive circuits are lagging circuitry. Why lagging circuitry? Because current always lags the voltage, and if it is purely inductive circuit, the angle is exactly 90 degrees, but practically speaking this angle will be somewhere between 0 to 90 degrees. Okay. Similarly, when we talk about capacitive circuits, you can see current is leading in this case, and ideal capacitive circuits we have this angle as 90 degrees, but practically speaking you'll have this angle somewhere between 0 to 90 degrees. Okay. Now when we talk about power also in case of purely inductive circuits and purely capacitive circuits, since in case of purely inductive and purely capacitive circuits this phase angle was 90 degrees, cos of phi was equal to 0. So we said that the power consumed in purely inductive circuits and purely capacitive circuits is 0. But practically speaking, there will be certain loss because this angle is not going to be now between, it will be between 0 to 90 and not is equal to 90 degrees. Okay? Yes. Now let us start with RL series circuit. Now when I say RL series circuit, you can visualize the very first half of the diagram. There is a resistance connected in series with an inductance, okay, and that is connected across a AC voltage. It is written as V is equal to Vm sin omega t. Okay, not to again forget that V is written in small letters because that is denoting instantaneous value. Vm is shown in capital letters because that is showing you a constant value, that is maximum value attained in a cycle. Okay, and sine of omega t, right? Now a point to be noted over here is current throughout the circuit is same, but whatever is the voltage applied to the circuit will now be coming across the resistance and inductance series combination. Okay, to another way to put it up will be the phasor sum of resistive drop and inductive drop is going to be the total voltage whatever is applied to the circuit. Okay, yes. Now when I say phasor sum, again let me just remind you, it is not algebraic sum. So it is not like if I am applying 20 volts, so it will be 2 plus 18 or 16 plus 4. No, this is algebraic sum. Okay, we are talking about phasor sum, isn't it? Okay, so phasor sum means we are going to add them on rectangle, right? Rectangle or parallelogram. Yes. To move ahead, let us say we are denoting the drop across resistance as VR, drop across inductor as VL, and the total voltage across the circuit, let us say supply voltage is V. Okay, so this V is going to be the phasor sum of VR plus VL. But since the angle, the phase angle between them is not 0 degrees as we have in resistive, right? In the resistor circuits we have the phase angle 0. Okay, but over here when we talk about VR and VL, are they in the same phase? No, they are not in the same phase, but they have a phase difference of 90 degrees between them, isn't it? So to take into account this 90 degrees phase difference, we have this J operator. So what do you mean by J operator is basically 90 degrees. Okay, when I say plus J, it is showing that the particular quantity is 90 degrees ahead. When I write minus J before that quantity, I mean to say that thing is lagging by 90 degrees. Okay, so what do I mean by VR plus J VL is that VL is leading ahead of VR by 90 degrees. Isn't it the case in case of inductive circuits? Current is lagging, isn't it? So it will be VR plus J VL. Okay, so one thing to be noted over here is you can see in the second half of this phasor diagram, it is taken as current, which is reference phasor. Why current is taken as reference phasor? Because we are talking about series circuits. So whatever is the common quantity is normally taken as reference. Okay, so here reference phasor is taken as current because current is the common quantity for all the elements. Okay, so in the same phase as current will be the resistive drop, because that is speciality of resistive drop, that the current and voltage are in the same phase. Okay, and to this current 90 degrees leading will be VL. Why? Because in the inductance it will be the current which will be 90 degrees lagging. Now here you might wonder, why am I talking about 90 degrees? Because I have already taken into account the resistive drop, isn't it? So now when I treat the resistance outside, now I can treat the inductor as positive, as a ideal one. Okay, so that is why treating it as ideal, I have shown the angle between I and VL as 90 degrees. Okay, so you can see we have VR plus VL. If you add on the rectangle, you get that you get that resultant phasor as V. Okay, and this V, if you just write VR as IR and VL as IXL, okay, we are introducing a new concept over here, is what is called as impedance. Okay, so that impedance will be taking care of resistance as well as inductance. Okay, to be more precise, inductive reactance, right? So V can be written as I into Z. Now if you just go ahead, we can see over here V is equal to VR square plus VL square. Okay, we are doing it rectangular addition, right? We are doing it on the rectangular this thing, because it is a phasor sum, right? Now if you substitute VR as IR and if you substitute VL I as IXL, you can take that I common and it will be under root of R square plus XL square. Okay, so that we can have V by I is equal to R plus JXL. This V by I now can be written as Z, where Z is called as impedance. Okay, impedance, IMPEDANCE, impedance of the circuit. This is in ohms, of course, can be now written as R plus JXL. Okay, again cos phi will be equal to R by Z, tan phi will be equal to XL by R, or phi can be equal to tan inverse of XL by R. You can see this from the impedance triangle. Now what is impedance triangle? Basically, let me come back to this diagram. So this is VR, this is VL, and this is IZ. Okay, so that is total voltage V. Now if you substitute VL as IXL and VR as IR, all the I's cancel, you get R, XL and Z. Okay, so that Z is equal to under root of R square plus XL square, or this cos phi will be equal to, it will be R upon Z. Okay, or this phi can be tan inverse of XL upon R. Okay, so for we have voltage triangle as VR, 90 degrees to it will be VL, and the resultant will be the total voltage V, supply voltage V. Okay, this is what is called as voltage triangle. And if I deduct all the I's, I'll get impedance triangle as R, 90 degrees to it will be XL, and the resultant will be Z. Okay, so this is what is called as impedance triangle. Okay, from impedance triangle we get that cos phi is equal to R by Z, or phi is equal to tan inverse of XL by R, or Z is equal to under root of R square plus XL square. Okay, yes, let us go ahead. So I suppose we had gone up to this. Yes, now let us talk about power. So power is equal to VI cos phi. Okay, so if I want to write in terms of instantaneous form, I'll be writing I as V as Vm sin omega t and I as Im sin omega t minus phi. Why minus phi? Because we are talking about inductive circuits. So in this case now, this phase angle will be minus, but no more it is 90 degrees. Okay, yes. So let us talk about power. So power will be equal to V into I. Substituting this as Vm sin omega t and Im sin omega t minus phi, you can go ahead with the derivation slowly. Okay, so all mathematical treatment, you can get Vm and Im out, and it will be, okay, twice of sin of omega t minus phi into sin omega t. This will be by 2. Okay, and if you just continue with this derivation, what do you get? What do you get? See, we get power as the product of RMS values of V and I multiplied by cos phi. Okay, so one thing is you can find out power as the product of RMS value of voltage multiplied by RMS value of current multiplied by cos phi, or another way will be you just find it out as I square R. Okay, cos phi can be found out as R by Z, as I said from the impedance triangle, if you remember. Yes, yes, that is what I was talking about. So you can also find out power as I square R. You can as well find it as VI cos phi. Okay, yes. You can see the power waveform over here. This is the voltage waveform. Okay, the one which is shown in turquoise color. Okay, then this is the current. Okay, you can see over here when the voltage is starting, the current is starting now. Okay, so there is a phase difference of pi by 2, because when the current is starting, it is voltage which is already at 90 degrees. Okay, so that is why the phase difference is 90 degrees. Okay, then we just go on like this. Okay, so you can see the power peak like this. Because why is it like this? Because it is VRMS into IRMS into cos phi, right? Okay, so the power peak is very small over here. You can see the voltage in this region is this, and the current in this region is this. So the product multiplied by cos phi is going to come like this. Okay, if you find this pi by 2 to pi region, see current is again in positive region, and voltage is also in the positive region. You can have this pick a greater one, right? Because it's a product, and so on. Okay, so this is how the power waveform goes. Okay, the next is, yes, so this is how the RL circuit behaves, RL series circuit behaves. Before we go further, let me have few solved problems so that the things will be clearer in your mind. Okay, a coil having a resistance of 5 ohm and an inductance of 31.8 millihenry are connected across 200 volts 50 hertz supply, and you have to calculate current drawn, power factor and power. Okay, the very first thing in case of RLC circuits, any AC circuits, is first you have to find out whether the values of reactances are given or inductance or capacitance is given. Okay, so you can see over here the value of inductance is given, but you'll have to convert it into reactance, right? Why into reactance? Because then you can find out what is the value of Z, isn't it? So first thing is you'll have to calculate XL. So XL can be calculated as 2 pi FL, where pi's value you have to take it from directly calculator, not as 22 by 7, not as 3.14. Okay, mind well. So it will be 2 into pi multiplied by 50 hertz, because as long as we are in India, the frequency is going to be 50 hertz. Okay, multiplied by, it will be 31.8 into 10 raised to power minus 3, because we'll have to convert this into standard form. What is the standard form for inductance? It is Henry. Okay, so 2 pi into 50 into 31.8 into 10 raised to power minus 3, that will come out to be 10 ohm. Okay, now we can talk about Z is, since it is RL series circuit, it has to be R plus JXL. Okay, remember it, impedance triangle. Okay, so R plus JXL, so R is given as 5. Okay, 5 plus it will be J10. Okay, now this 5 plus J10 can be converted into polar form. Okay, now how do you convert it into polar form? Okay, what do you do is, I'm talking about 991 ms right now. You have to shift, then the second last row, second last button, you can have keys like rectangular bracket and polar bracket. Okay, now expected thing is to be pressed. Now when I say 5 plus J10, what is this form? This is rectangular form. What is the expected form? It is polar form. Why is the expected form polar form? Because I want to do division as V by Z as current. Am I clear? Okay, so what will you do is shift, it will be, now what is to be pressed? I want polar form. Okay, the second last line, second last button, so I'll be getting shift, this second last button. What do I get on the screen is polar bracket. Okay, and here I'll be pressing it as 5 resistance, comma, okay, comma, you can see on your calculator, comma, it will be 10 is equal to, what is it, 11.1803. Okay, then you have to press alpha, that is the button by the side of shift, alpha F. is equal to, you will be getting 63.4349. okay. Normally these values are to be calculated up to 4th decimal. okay, so this is how you convert a rectangular form into polar form. okay, and whatever then z you have in the polar form, you have to just do it as I is equal to v by z. okay, and whatever z's angle you will be getting, you will be getting minus angle, minus of it for the current angle. okay, and when the current angle is minus, it automatically says that it's a lagging power factor. okay, and whatever is current's phase, power factor of the cos of it will be giving you the power factor. okay, and the last one is power is equal to vi cos phi. In this case the RMS value of voltage, that is 200, multiplied by RMS value of current. You can have this current's value from the v by z, whatever division you have taken, and the polar form's magnitude. This is what is the polar form's magnitude of current. okay, multiplied by, this is current ka jo, whatever is the current's angle, the cos of it. okay, so that is 0.447, so that comes out to be 1598.47 watts. okay, so that is about the power. This is regarding RL series circuit. okay, if you have any kind of query, feel free to write in the comment section. okay, thank you. Let us meet again for RC series in the next lecture. Thank you.